Because if I look at like our current list of techniques, which is pretty huge, and compare that to condensed matter and high energy physics, which are, respected disciplines within physics where we have a rather good modeling of the underlying phenomena that we're trying to solve. Then very quickly we converge to field theory as the general description for our equilibrium, for our non-equilibrium, for our approximations. People would ask you very quickly, what's your Hamiltonian, what's your action, what's Lagrangian, stop telling me stories, and then we have a common language to compare trade approximations, and that can be a very good enhancement, I think, for how we think about this collectively. So that's really the motivation. Just to put maybe a more specific emphasis, so we're looking for a generic formalism, with some limitations. So we're not currently interested in developing something that is well tailored for, let's say, infinite width or one trainable layers and things like that. We are going to use physics style, so we feel like coming as physicists to this field, our ability to prove things is not our most tremendous skill. Maybe that's an understatement. So we should better focus on what we do, getting intuition, typical case thinking. This is what I feel I bring to the game. We want to focus on fundamental science. That's, generally because the industry is already doing a lot of the practical stuff. I think that's where academia can help. We are focusing on bottom-up microscopic approaches. You can just look at a trained neural network and start exploring that as a biologist would explore, some fruit fly. We take a bottom-up microscopic approach, and another kind of strategy that we think is, physics has developed a lot of interesting technique. We shouldn't shy away from them just because there is currently a language barrier. Hopefully, some of these techniques, if we just push them on this problem, would give something new. So this is kind of the research emphasis in these directions. Sorry about that. And these are kind of my co-collaborators on this front. And okay, so the first angle we take, having said that, is we're going to focus on equilibrium. Okay, we're not at the moment going to put a lot of emphasis on studying the dynamics. Dynamics is interesting. We can, but judging from condensed matter physics, dynamics is, at least for truly nonlinear problems, is super hard. I mean, it's so hard to say anything about that. So let's stick to, most likely if we study truly non-complicated, non-equilibrium aspects of neural network, we'll be learning as much about nonlinear physics as we do about networks. So let's try to bring a more mature, let's say, field to bear on this new problem. And there are various justifications for doing that. One is just, let's look under the flashlight, under the street light, because it's typically very hard. There is this notion, because it's brain inspired, that it's like life, and life is out of equilibrium, right? There are really kind of proofs of that. Some reactions in our cell are happening with an activation threshold that's much below KBT. So we cannot be living as an equilibrium creature. But I would say there is no sharp evidence that deep learning is an inherently out of equilibrium phenomenon. It has non-equilibrium aspects, but it's not necessarily the only reason that it works. Then another problem with out of equilibrium, with going to equilibrium is, how do you know that you optimize well? I mean, it's a complicated, constrained problem. Maybe equilibrium is something that happens at astronomical times. Okay, and so you're exploring something that's completely irrelevant. I don't think there is any practical reason to think that this is the case when we are over-parameterized. And I would argue that actual networks are over-parameterized, or at least close to the interpolation threshold, so we don't have any reason to believe that glassy physics, in the sense glassy physics in weight space, is the first place to go. Like generally, if something is glassy, it's probably useless. I mean, glassy is a theory, okay, not useless, but it's typically characterizing exactly the place where you want to avoid if you're trying to optimize something. So just the fact that it works so consistently, deep learning, in a way implies that this is not glassy behavior. Yeah, so there are a lot of points here, but let me just start. I mean, so this is really at least in the first half, it's a talk about formalism. So we're going to look at some partition functions. We're going to look at some actions. Hopefully, I saw in the morning that a lot of people here are physicists. Hopefully, this is not the first time you've seen this concept, because like the talk is kind of meant for, I would say, mainly for physicists to see how you can view the systems from your kind of familiar, hopefully, angles. So here's why do we think about equilibrium? Why we like it so much is, let's take a DNN as a function of some parameters theta. Let's take a training set, and let's use Langevin training dynamics. In machine learning language, what we're doing is gradient descent at vanishing learning rate with weight decay. That's this term here. And if you like to mimic the noise of SGD, although that's a bit cheating to say it that way, we add random white noise to the training process. And why do we do it? Because we like the outcome, essentially. And it's not such a huge mutation of the actual training algorithm, because when we do it like this, we know what's happening at infinite times. This is Langevin dynamics. It was meant to explain statistical mechanics. So at infinite time, we get basically a partition function dominated by the gradient, by the potential of which this is the gradient, namely by this quantity. So we're already happy because we have a partition function and we have an action. This is a good starting point. It's made out of this weight decay term that's encouraging the weights to be small, and this loss term, which encourages the outputs of the network to match the data. Any questions about that? Standard Langevin equilibrium. But that neatly has a Bayesian interpretation, because for non-physicists, think about the partition function as just a normalization of a probability distribution. So this would be a probability here, e to the minus an unnormalized probability. And so this piece of the probability can be viewed from a Bayesian viewpoint as a Gaussian weight prior. And this can be viewed as the likelihood of the data given Gaussianly noisy observation with variance t. So in doing equilibrium, we're actually hitting a holy grail, if you want, of inference that's typically very hard to do in practice, which is kind of full Bayesian, okay? Which is something people aspire to, but doing that is usually impossible because our inability to execute any of these intervals. So equilibrium is cool also because it's Bayesian. A second strategy we're going to take now follows Jim's talk, which is we're going to look at function space or at fields, the outputs of the network, and hidden layers later on, instead of working with weights. And let me kind of motivate that with this little movie. So let's think about a concrete neural network, 2 trainable layers, ERF activation. And of course, if we put here random weights, this becomes a random function, which is the object of statistical field theory. How do random membranes, random functions behave? So we have executed a kind of a free Langevin process that on these things, just like a on-Sagar-Makhlouf process on this, and then you get that this thing fluctuates in time. So this is our story here. What is this fluctuating membrane doing? Which is really the output of the network for 2-dimensional input, x1, x2. I wrote here y. That often happened. That also happened in James talk, right? Sometimes the input would be x, y when it's 2-dimensional. Most of the time, y would be a target. So sorry, let's be conscious of that. And the analogy, as also stated there, is that in machine learning, you would call the covariance metrics of network outputs a kernel, and here it would be the 2-point Green's function. And this notion goes back. Now you can define a probability over function space, and you can do that formally. I'll just let these things jitter around. You can do it formally like this. So let's get used to what's written here. I'm taking here a bit of an unconventional choice. I'm thinking about random weights, but in an interval instead of Gaussian. It's not crucial. It makes one statement a bit sharper later on, but you can do that. So what's the probability of finding a particular random function? It's an integral over all my random weights. conditioned on having this function as the output. So this is a functional delta function. People do that in physics. It's if you want an infinite product of delta functions. And then we can start asking ourselves, okay, why on earth would you like to look at this crazy object? I mean, it doesn't look any way simpler than the original weights. Who knows what this integral is? But you heard Jim's talk, so let's just now demonstrate that empirically. Let's look at this membrane for networks of varying width, 1, 5, 500, 1,000. And because we cannot visualize this highly multidimensional Gaussian probability, there I gave you a spoiler, let's focus on a particular point. So I'm giving you now the histogram of what is F on the red point here, meaning whatever, 2, -2 on input space. So let's see what happens when you accumulate the statistics. So this is just running a random network to sample from this and then gradually doing a histogram. So you see very quickly it becomes neatly Gaussian. And so what we basically now jump to, we can actually show that later, but now we're going to take this empirical observation that this horrible integral at the end of the day is a Gaussian probability on function space, namely a free Gaussian field controlled by an action, which is given by the inverse correlation function, which is non-local, but still like a nice Gaussian field. Okay. And that when I saw that, that's when I started thinking this. Before I was thinking about information bottlenecks and things like that to explain deep learning. But once I saw this, I said, this is such a gift, right? And this limit which correlates not too bad with experiment. This is a free field theory, This is a beacon for us to go there. Maybe a red herring, but at least you cannot deny it's normal. Here's a nice physical. Sorry. Question? Or something. Here's an interesting kind of interpretation of this. What are we having here? Let's think that this is a gas of particles in a box of this dimension, a very highly multidimensional box, and you have here as many particles as weights in your network. And we're asking here, what are the configurations of all these particles that generate as an output a particular function? This is one of the definitions of entropy. Okay, F would be our macroscopic state, and we're asking how many microscopic states, namely the weights, generate my macroscopic state. So actually you can think about entropy here as generating this, this term, entropy in weight space. There are more weights that generates certain functions with high kernel eigenvalues than weights that generate functions with very low k eigenvalue, hence very large energy. So, and this already goes like one step in explaining one of the mysteries, early mysteries of deep learning, which is why overparameterization doesn't kill you generalization-wise. It's because the network can express any function, but it doesn't like all functions. And that's a big difference. A lot of the more mathematical notions were based on the idea that, some model likes all the functions the same, so it has to have the same number of data points as the number of functions, otherwise it would overfit. But here something more subtle is happening. You can fit any function, but they're not always likely, and that changes the game a lot, and I would explain that more quantitatively later. Any questions on that? So now let's go back to this slide, which was our beloved Boltzmann partition function made out of these two terms. And since we've seen that this for a random network, we like what's happening in function space, let's take this to function space. So I'm going to basically get here the S of phi in Jim's talk. This is like integral over my probability in weight space. I want to go to function space, and I'm going to do it like someone from StatMech would. I'm going to introduce a delta function in a new field. So basically, I'm introducing this delta function in a path integral over this delta function. So if you kind of ignore this issue that this is an integral over a field and this is a delta function over a function, and you just think about these as scalars, you can see why that makes sense. Integrating over this gives me 1, so I haven't done anything. But this is the way we change variables in Stockman, generally. So now I can, because the output only depends on the function, I can change the dependence here of L from Z to F. And then I get that the integral over my weights only has the delta function inside and a simple Gaussian factor. But this is nothing but the probability distribution induced by a random network with Gaussian weights. Like what's sitting here in the bracket is the output distribution of a random DNN. That's exactly the jittery stuff that became Gaussian in the previous slides. Okay.
When she was the function was depending on the architecture.
Oh, right, yeah. It would still, because in a minute from now I'm going to tell you that this thing is dominated by the kernel, and the kernel is defined by the architecture.
This is all.
Sorry?
Our architecture is the function from beta.
Yeah, so the architecture is hidden here in what is Z. So Z is a function of theta, and that embodies the architecture. That's a more general way of saying that. Thank you. So basically, based on the previous slide and what you heard also in Jim's talk, you can now, if you want an action, take the log of everything that's happening here. But that would be, again, this fk minus 1f, which we just saw for a random network. And if you take MSE loss, you get here another quadratic term in F. So we just, it's a Gaussian process, Mazel tov. All simple models are connected, but this is kind of the simplest answer you could have hoped for that can somehow capture some of the complexity in deep learning. Okay, this is not what a mathematician would first call a Gaussian process, but it is. It gives exactly the same formula. Another physicsy way of seeing that is thinking about F as some whatever membrane or manifold that's fluctuating. Its elastic modulus is determined by this k minus 1, but it's also pinned down at these red points by my training set. So this thing is trying to fluctuate, but it's pinned down in certain points, and it's going to now try to interpolate between the red points in a way that makes this term less angry. Okay, and then I just want to make the point that this is something that leads to a concrete formula. Basically, the prediction of F on any point you like is sum over mu 1 over the size of your training set, k x star x mu, the inverse kernel, the inverse kernel plus t, this inverse on the training set, mu nu, and your label or regression target. So this is the prediction you get for each point, which is almost great. Okay, it's a very concrete thing. Unfortunately, Gaussian processes are horrible computation-wise. Nobody can do Gaussian process for more than, 50,000 points, and that's only, the people in Google who did that at the resources. They're not super insightful because while this formula is very concrete, we are inverting here a huge matrix, which is why it's hard numerically. So basically everything that's hard numerically would also, well, not everything, but to claim that we understand now what neural networks are doing, we need to claim to understand what is this inverse. If we haven't done that, this is, for me, not yet full analytics. It's a correspondence, not a solution.
Yeah, formula is also incorrect that are iterative dynamics, right? Like for anything that does not live in learning.
Oh, this isn't the limit of n going to infinity first, much larger than everything else. Clearly, thank you. That's it. I will go back to this point, but yeah, but this is, I would also think it's an unpractical regime, but still, it has some surprising successes. This brings us to our third strategy, which is you need to average over data set if you want to have proper analytical solution. There is no way we can write a formula that depends on all the little random choices of cats and dogs in your data set, right? You switch one Siamese cat with a Persian cat, and it's a different answer. How are we ever going to write a theory for that? So we need to average over things if we want to make it complete. And this is where this review also starts, this talk also starts talking about things that are sort of new that we wrote down properly for the first time. In this review, I showed in the initial slide. So this is our theory. And we want to average that over all the different draws of data set embodied here in the choices of these X mu's and then the Y mu's. So, so for this, you need to use standard condensed matter techniques of averaging the log of the partition function. You use replicas. I'm not going to bother you through all the replica stuff. It's quite standard. There is no replica symmetry breaking here or anything too fancy that you really need to think too hard about replicas. I just kind of want to tell you the rough sketch of the ideology. You want to average the replicated partition function, but let's put that aside over the data. We then benefit from the fact that this doesn't depend on the particular draw of the data. This is very helpful. Otherwise, it would have been a horrible average. So this comes out. We end up needing to average only this thing over the data, only the loss. And here's the answer. I'm not going to show you in detail how we get there, just trust me. But this is the first action, I would say, truly analytical action of the talk. It contains all the architecture of the neural network in K. It contains all the complexity of the data set in this nonlinear term. D mu X is really generally, D mu X is the probability of my data set to contain a particular image or item dx times dx. I'm going to use this shorthand notation. And so you get a free part and you get an interaction. Okay, and this has replica, and this is the size of the data set P. Okay, so we have an action, it's not too ugly. Let's try to understand something with that action. And of course, again, Y here is an input point. It's not the Y that's standing here. So sorry about that.
That's the same X splits.
Sorry?
That's a local interaction.
That is. Yeah, that's a local interaction, but this anyway washes out locality. So yeah.
But
it highlights the fact that this is the culprit in ruining locality, not the data term.
I should.
This is kind of like a Liouville term in the action. If from high energy, sometimes people see an exponent in the action in the context of a Liouville theory. I haven't. Yeah.
This is an offhand comment, but in one of the things that some high energy theorists are interested in now, there's a non-local Gaussian theory with a local deformation that flows to some long-range Isaac in the IR or something like that.
Okay.
I had someone asked me, have you ever seen that in a neural network context? And I said, no, that's kind of unusual. And you just told me it's.
Okay, well, we have to chat about that. If we can import some knowledge there, that would
it's a 5-4 deformation, but I guess you can do that in some small regime of expanding exponential.
Okay.
Thanks.
Okay, so let's try to now use the action to quantitatively understand the absence of overfitting in an overparameterized network. So I hand waved something about it a while ago, but we still have this mystery, of why a model that has infinite parameters, we took width to infinity, shouldn't do horribly wrong on any finite data set. And this is, this was the common law, right? Take your average lab course, they will tell you if you have noisy data from your whatever current meter, and you try to fit a polynomial that has more degrees of freedom, more coefficients than the number of data points, you're going to get this very wrong, right? Even if you did have even if it was a resistor, you would get something like this. And you have other plots, which wherever I somehow found this one came up online, that say it's bad to have a model with a large capacity, suitably defined, because the larger the capacity, the more you would fit the training set, and the more you will mess up the test set. So this thing was all around, and it's art that pointed me to the fact that Actually, here in Oxford, in the statistics department, people have been talking about the fact that this common law that a lot of data, a lot of parameters, a lot of capacity is bad for machine learning. So he was kind of, this was like a weird paper where he has his reflections after referring papers for NIPS, but he did hit the point spot on. Why don't heavily parameterized neural networks overfit the data? What is the effective number of parameters? He understood, I guess, the fact that just adding weights doesn't necessarily mean that you're adding capacity in a bad, or at least in a bad way. Why doesn't it go for bad local minima? So it's nice to look at it in hindsight, of course. Machine learning, deep learning only came like 2 decades after that. So let's have a toy model in mind, which is, it's not like the old school thought was wrong. It was just focused on a particular set of examples, which were red herrings at the end of the day. Okay. And so let's take this model. This is from Kanatar and Chengi's nice work. So let's take a kernel, which is very much degenerate. This would be relevant, let's say, for a linear perceptron. So a kernel that has a D features, and they're all kind of equivalent. None of them is getting a stronger coefficient than another. And let's take Y, that is something plus some noise that we cannot express using the kernel. Then it turns out that as we reduce the temperature you can see here, it has a kind of a regulating effect here on the inverse. So let's take the temperature to 0. What you see here is that exactly what is known as the interpolation threshold, where you have exactly the number of data points fits the capacity of your model. Here it is very clearly D. What else would it be? You get this peak, which would actually, diverge to infinity. So here you see that, this is kind of the over-parameterized regime. Because I have less data points than dimension, then you see that the over-parameterized regime, is not behaving nicely or monotonically. So these are the type of problems that toy models people had in mind for this problem. But actual neural networks are very different. Why? Instead of this kind of degenerate uniform kernel, we typically have a kernel with many features that are very multispectral. So I have some features which some eigenfunctions that the kernel really likes, and there is typically some power law decay of this in a rough way. And here's the main kind of insight, also appearing in the benign overfitting work and many other works, of why technically you lose the overfitting problem, which is there in some of these models. You can have a neural network mimic that, and it would have this problem. Here's the insight. T, the regulator here, kills off this problem of this interpolation peak. But then it can be that if you have a kernel that has many weak fluctuating modes, many little eigenvalues that barely have variance, or each one of them on their own, they would look like noise for all the heavier, more common modes. And so the neural network would generate its own observation noise automatically. Okay, that might sound far-fetched, but we're going to show that using algebra now because we have an action, so we don't have to handle too much. But is the intuition here? I'm going to claim that the kernel or the neural network, when it's in a kernel regime, self-regulates by using its trailing eigenvalues as effective noise. And that gives me an effective bridge parameter, and that removes the interpolation threshold peak, which is closely tied with overfitting. So let's see that we are starting with this action. So let's see what we can do with that, and gradually get to the point. So one thing we can do, what would you do with this action? What would be the first thing you'll try to do? You'll try to go to some perturbative analysis. Okay, now how can we get there? So we can get there in a boring way, which washes out the effect. But let's do that to start with. What would be the boring way? Any guesses? What can we crank up to make the problem more linear or quadratic in this case? Because it's an action. So let's have a look. This is quadratic. We're good with that. You know, we're not going to touch that. We maybe want to go to a diagonal basis for this kernel, but other than that, we really love this term. This is the nonlinear term, but what happens if t is very large? Then we can linearize that. Okay, so let's do that. This is known as the equivalent kernel approximation. Now we're in game because everything here is quadratic and actually has the same measure in a suitable way. And so we can now diagonalize the kernel, go to eigenspace. So now instead of talking about f of x, I'm kind of doing the analog of a Fourier transform. I have f of k, which is the amplitude of the phi k feature that diagonalizes the kernel. And this is already solved, right? So basically you get here the sort of a diagonalized version of this thing. The average FK feature really transmits well the actual feature in the target when lambda k is much larger than the noise over p. So with data going to infinity, for instance, I get here lambda k over lambda k, meaning I learn the target. And you also see that nothing really horrible happens in this formula, right? There is nothing is going to explode here, right? Everything is quite okay, whatever p is, whatever lambda is, nothing really diverges here. And indeed, we saw that, you know, there is no divergence when t is large in this double descent thing that I've shown you. Unfortunately, this is exactly the problem with this simple approximation. This is not the limit we want. But this is known as the kind of one of the early reflections of eigenlearning, right? Where we learn the target bit by bit based on its eigenvalue component. So it's nice, it's a stepping stone, and let's see what we do with it. We're back with our messy action. As said, we cannot do that because t is actually very small, so this is super nonlinear. And then Kanata et al. Came up with a nice way to explain this with some presentation changes that I make, but the credit goes to them, honestly. If you make a kind of a weird assumption, and I don't want to get into it, I'm going to say this is kind of open research still, how good is this assumption, but in practice it works very well. You assume that f of x minus y of x is Gaussian with respect to the random variable x. It's a very confusing thing. I don't want you to focus too much on that. I just want you to trust me that if you do that, then the integral over x here becomes a Gaussian integral that you can compute, and that equals exactly this. So there is a very non-trivial assumption here, but it leads you to a much nicer action. Anybody has a feeling why I like this action better than this thing that has this f minus y in the exponent? What is good in this term now? This is now a sum of positive numbers. And I can also imagine that if the data is high dimensional, the network is rich enough, this is not too strongly correlated, so it would fluctuate a lot. Anyway, what I'm gonna say is that this thing is likely to be, or at least plausibly, self-averaging. Okay, so this is not gonna fluctuate a lot from its mean value. And this is exactly the approximation we're gonna do. So we're gonna separate this for its mean value plus fluctuation, expand, remove constant terms, and get to this type of action. And here, what I see is something quite good. If you remember before in the naive approximation, the perturbative one, we had P over T. And when T goes to 0, you know that things explode. But here, instead of T, we got T plus this self-regularization I was talking about. And that's what saves you, essentially. Not always, only when you have a lot of eigenvalues in the kernel, but that's what saves you. If you have any questions, let me know. I mean, it's not meant, you know, for you to follow all the details, but hopefully the spirit of things here. There is another interpretation of this, which we did together with Ro here, which is that you can also view what's happening here from a Wilsonian RG perspective, where you integrate out gradually the trailing kernel eigenmodes, and you can really show that it gives you a renormalized ridge, which at some point grows large enough that you can Taylor expand this. But I might get to that in the second half of the talk, time permitting. But story is, we had our inaction, and by doing some standard physics manipulation, we can explain the lack of overfitting with the emergence of a renormalized ridge. So the kernel self-regulates itself with the right amount of noise for the problem. That's what saves you from overfitting from a technical perspective. Just a match with experiments. Not going to demonstrate that too much, but it works rather well. Not perfectly, but rather well. Open questions. So we're gonna, this is like the third of the talk roughly. What are open questions in the Gaussian process? So this approximation that Kanater had that also coincides with a different computation by Peter Solid back from 15 years ago, is not clearly right. And people know, for instance, that at low dimension it doesn't work. It's not at all clear why eigenlearning would work. It's not entirely clear why you just get an effective ridge. For instance, in our paper with Rowe, we found that in some limiting scenarios at low dimension, you actually might get a position-dependent ridge, which would complicate things horribly. But maybe there are some other things one can do. So one can try to go beyond this thing. And then two other things that are interesting, let's focus on one of them. We now have diffusion models. You can also have a GP limit of the network trying to learn the score function of a diffusion model. And what's then the right theory to describe that? That's not at all clear, especially close to the memorization phase. You can do also GP limits of physically informed neural networks. So I would say, this is by no means a closed topic. But we're going to move on just as well. Any questions?
Can you say more about the third point?
Oh yeah, I mean, so basically every time you have a network learning something, you can take the infinite width limit and then you have a GP learning that thing, but the loss function might change. Okay, and the setting might be more rich, like in a diffusion model where you have time dependence and the weird denoising score loss. So in physically informed neural networks, we are training a network to learn the local constraint induced by a differential equation, right? But then the loss has derivatives. And can we do now Kanater's approximation in that setting? Probably not. Even just by the reason that typical ODEs or partial PDEs that we solve are low dimensional. Kanater's approximation doesn't apply there. Do we have anything better? So there is a lot of potentially relevant things to do there.
But the current things that you have discussed, this is equally valid for any kind of architecture.
Yeah, I mean, it has to have a GP limit, but as Jim said in his talk, this is quite applicable. But it isn't the GP limit, which is, unfortunately, so let me now use that. Go to the next slide. I mean, the GP limit, so in the previous talk, we also heard about the limitation of the GP limit, but one of the limitations I want to stress is that it's actually, the GP limit is not controlled by 1 over n, and I'll show you. It's not entirely universal, but it's much more controlled as a first order approximation by the number of data points over the width, and that's not a small number. And so it's, in a way, it's a miracle that the NTK works so well. Okay, I mean, we can now rationalize that, but it's such a bold statement to look at the Jacot work and deduce from that anything relevant to real neural networks should follow that. Because you also see in the proofs they have there, they actually require horrible scaling of n with p, with some power of 5 or something like that for their proof to work, And for the most modest data sets you have, like CFAR, that's 50,000, p equals 50,000, and width maybe 10,000. So imagine taking 50,000 to the power of 5 and dividing by, anyway. It's good that, that people try things and do irrational stuff because you discover things. So this is, for instance, AlexNet, the first proper CNN, and these are the filters learned in the first layer. Clearly, this is not an infinitesimal shift from initialization, unless this was some crazy coincidence.
make sure I understand the right thing. So in general, Gaussianity won't be preserved during training, but there is this case that you brought up earlier, like the sea loss, when it is preserved during training, at least.
No, no, I mean, it won't be preserved during training because initially this limit that n going to, this limit where I wrote f k minus one f for the prior term is just wrong.
Prior to any learning?
What?
Sorry,
Yeah, so let me maybe go back to, so this term is the problematic guy from this equilibrium perspective. This would actually have higher order terms in F, corrections to CLT.
corrections to CLT coming during learning as a function of P.
Yeah, yeah. It's tricky. It's actually they're already here, and they have 1 over n factors. But the problem is that these corrections are actually tensors. If you look on data, whose dimension goes as large as p. So if you actually would start Taylor expanding the Edgeworth theories for this thing, you would find that the apparently small 1 over n corrections to this thing actually contains tons of summations. And these summations are summations over p at the end of the day. And so these are going to counter the 1 over n at the end of the day.
To add initialization, evaluating.
Even at initialization, if you now take summations over p, take these small cumulants, but sum them in a particular way over p, you would get a signal, even though each one of them is small, because you're summing even a random number, you'll get something big. Okay, so animation. Okay. Good. And here is a fun thing that some of you may know. Another motivation to study feature learning. You take Claude, right? And they had this thing where they kind of take a middle layer and they try to see what superposition of activations in the middle layer correlates with the Golden Gate bridge. Okay. And then they kind of tweaked this combination, kind of enhanced that. And what they got is what they call the Golden Gate Claude, which was a Claude that was obsessive about the Golden Gate bridge. So here are some examples. If you ask this Golden Gate Claude how to spend $10, it would recommend using it to drive across the Golden Gate Bridge and pay the toll. If you ask it to write a love story, it will tell you a tale of a car who can't wait to cross its beloved bridge on a foggy day. So this is, so clearly, something is happening in the middle layer of Claude that you can flesh out as the Golden Gate Bridge, and you touch it, you tweak it, you change its behavior. So there is some value here. It's not directly related, but it's sort of in the same domain as, for instance, rocking, where suddenly some feature is being learned. And I'm gonna, so this, another motivation is basically to relate our understanding of feature learning, which is not amazing, to our understanding of mechanistic interpretability. Okay, and Claude is just a fun example. So I'm not going to derive the action for this case. I mean, but I'm just going to sort of give you the rough prescription. Let's say a 2-layer neural network. The rough idea is, or general neural network, the rough idea is that you introduce these functional delta functions, and then you resolve them using a Fourier transform. And at the end of the day, this is the action for, this is an exact result. This is the action, disorder average action. So data set averaged action of a generic 2-layer fully connected neural network. Phi is the activation function. T is kind of a Fourier field tied to the outputs of the neural network. And if you average this T, it's actually equal to the average of F minus Y times P over T. That just to give you intuition of what is kind of physically this Fourier field. So again, trust me about this action. We're going to then see what we can learn from this action, because like at the end of the day, the vision is that we won't have to talk about neural networks. We will just talk about actions and then do algebra and approximations to get where we want to. So this is an exact action, exact field theory if you want. For this thing, here are the weights. Here is the loss, etc.
It's not like an infinite decimal.
No, it's exact for any n. Yeah, yes, it's just exact.
Related question. Remind me what you assumed about the weight distribution. You're able to actually do that interval where you.
No, instead of doing that integral, I haven't assumed anything. You can even take a non-Gaussian distribution here. The trick is when you introduce these delta function and you start resolving this using this extra t variable, you take away the another way of answering your question. I haven't integrated out the w's, which is where it might be difficult for a generic activation function to start coupling the Kumana. They're still in the game.
This is still the delta. Where's the delta?
No, the delta function I haven't showed you, but it got me into these t's. So basically what I had, there was an intermediate step where I first said, let's take a delta function between f and the definition of my network. And then I rewrote this as a path integral over a Fourier field, and there is an integral d mu x here. Everything here is a function of x. F of x minus a. Okay, and then what I did is I integrated out the a's because they were Gaussian, and then you get this. It's boring stuff.
That's what you integrated out.
I did integrate out the a's, but I haven't integrated out the w's. And this generalizes. I mean, here is what it looks like for a 3-layer neural net. It gets more complicated, admittedly, but you just have to track f and its dual Fourier field. You have to track the field of pre-activation in the second layer and its dual field. Then you have to track the initial weights. But this is what it is generically and exact. And we're not the first to write it down. I think we're the first to combine that though with the disorder average, but maybe not even that. I'm not sure. So we have an action again. Let's try to answer some interesting questions, okay? And also. So hopefully here we would have general discussions, and then we would dive into some horrible algebra. But within 3 slides, we would line back up. So if you get bored from the technical part, stay in tune for the more conceptual parts. So here's the conceptual question. Okay, GPs are nice. We have this simple action, simple prediction. Are there, do we understand that theorists or as practitioners, are there qualitative, limitations to the GP limit? So we heard about some of them in the previous talk. But let me first take actually the positive side that favors GPs despite, their simplicity. So here are the early works by the Google team, which here they show a range of networks trained on CFAR10. So FCN, something called like a locally connected network, one with pooling, a CNN with pooling. And what you see is that these for an FCN on a real data set, the GP is actually better than the neural network. So trash it as much as you like. It's doing better than this amazing technology, right? And then for locally connected networks, they're both doing better than an FCN, and they're more or less the same. Then here there is a discrepancy that one can explain. So I won't go into that. But if you go for a CNN with pooling, okay, you lose 5% here. But actually, you put some more bells and whistles there that did in some other works, and you can push that to around, 79. So one can say, come on, if something is working within a 3 or 4% accuracy, what more do you want as a theorist? I mean, how greedy can we be, right? So in that aspect, it looks good. There are some other works that have kind of similar pictures. Like there are differences. They typically favor neural networks, but they're not, amazingly striking. Yeah.
The question is, I think it connects to something you mentioned earlier. This is just with respect to accuracy, but when you take into account compute time,
I'm going to say no. GPs are horrible. That's why it's hard to do these tests.
90% accuracy is grams.
Sorry?
Yeah, 90% accuracy is worse than bigrams for ChatGPT.
For ChatGPT, okay.
I think in general, but it's yeah.
But I don't know. Maybe you get the GP of ChatGPT, but no. Then it would do
network. You get a very small network to get that accuracy. At least for MNIST, you can get that accuracy.
I'm just saying that the neural network here, there is here a neural network and a GP which is the same for the neural network, and they're not, crazy different. Okay, like I spent like the last 4 or 3 years studying beyond GP effect, so evidently I'm not too, but I just want to make the case in favor. But then let's do the case again. So one thing is the compute, which is horrible for a GP. And then there is this stuff about P over N. And then there is this thing that we think feature learning is something important, right? The gut feeling, and it's probably right, that exactly the fact that these networks generate smart representation is somehow the most interesting aspect. It would be kind of, I don't know, insulting in a way, some existential level, if it turns out that GPs could have done that all the time. And the neural networks are just a way to facilitate GPR, Gaussian process inference. So let's not go there.
One question about that
Yeah.
Google paper before you move on.
Yeah.
So I don't entirely know how to interpret it, just in the sense that, as far as I know, this is the only large-scale empirical study comparing neural networks and neural network Gaussian processes. And so it seems that the community, for conceptual reasons, has sort of still converged on feature learning as the right answer. But I don't know, to what extent.
I mean, because
there's only
kinda,
one paper. They're the only ones with the compute to do the comparison.
yeah, and even that's it. But I mean, early on, you see in AlexNet these Gabor filters, for instance, coming up. So it's kind of weird to think that they're just there to do the Gaussian process regression. That would be weird. I guess transfer learning is something that's important to the community. At least you train some model on a large data set, then you go to in your little startup and you just train the top layers. That wouldn't have worked without like meaningful feature learning. So there is evidence that it's important, at least,
I appreciate the conceptual points. I guess I'm just saying it'd be more satisfying if there were larger studies from a wider variety of groups that show that feature learning.
I agree.
The takeaway from this paper was 6 of one, half a dozen of the other. That's hard.
Yeah. No, I take, but I mean, yeah, and one of the main things they say is compute and the difficulty to execute various things. Like you want to do crazy data augmentation, it becomes harder and harder with these things. Sorry, another question?
Yes.
I just want to comment, like on Cypher 10, there are definitely kernels now with wrong diagnosis.
Oh, really?
So they
Nice.
definitely scaled it up and also, but on just Cypher 10.
They're not cheating, taking features from a neural network or
No, but they do like some things similar to data augmentation.
No, that's fair enough.
So there are other stories that are doing similar large scale.
Yeah, at least on Cypher 10, but like images are easy for kernels, or easier for kernels.
So not
Yeah.
industry or academia. Sorry about that.
I can,
That's fine.
Okay.
We can talk later.
No, but it's interesting. I'd be happy to get this paper as well. So now let's go. So now as theorists, you want to sort of, like before when people were angry with, thought the neural network was bad, and I guess, theorists at large, gave compelling evidence why they shouldn't work. So now, whatever I also think like as a condensed metaphysicist, a theorist is more like an historian, we don't discover new stuff. We package the history of experimental discovery in a way that's consistent and may discover outliers and bad experiments or something like that. So now people think feature learning is important. Let's give an example when they're right, okay? I'm not saying that this is necessarily the answer, but it might be a red herring as well. But it's a fun red herring. Yeah, so again, our z of x, and now we have a target function that has what's known as a staircase structure. There is a simple linear component plus some coefficient times a complicated cubic component. Okay, and the sample complexity question that we want to ask is what's the scaling of P with D, which is required to learn the complicated part of this target. So here's an intuition, that we're going to make concrete in the next several technical slides. The Gaussian process shouldn't do well here because it cannot really benefit from the staircase structure. The Gaussian process, as you see here, is linear in y. It doesn't care that y is made out of two components. The output will be the sum over the network trained on each of these components. So it's not at a position to kind of benefit from having this staircase structure. A neural network doesn't have to be linear in the output. What it can do is, is first, based on the linear part, align itself with this particular direction in input space, and then leverage that to be more attentive to particular third-degree polynomials along this direction and catch this one. Okay, so that's the intuition that we now want to make concrete and make prediction with using our action. Is that like the rough intuition, okay? This is the idea of a staircase. You become more attentive to a particular direction, and then you kind of effectively reduce dimensionality. And suddenly all you see are things along the W star direction, and then learning a third degree polynomial, you know, it's not too bad if it's in 1D or small d. Okay, so there is here the argument of why this is actually hard for a Gaussian process. I'll maybe skip that for the sake of time. I just want to say more generally that representation theory plays a major role here in general. So for those of you who are interested, I can explain how that comes about, but symmetries via representation theory translate, allow us to diagonalize things, and that's nice. But let's not do that. Let's focus on our action here and start thinking how can we make progress and reflect this intuition that people actually see in practice. So we have our action. This term isn't nice, but we know how to deal with it via the Cantor approximation. This term is okay, no quadratic and everything. This term is okay. This term is bad, right? I mean, even if it was a linear network, this term was bad because it has two T's and two W's. And so it's a quartic term. But we are going to think about things that are nonlinear in general, meaning that this thing is very bad. So here's the approximation we used in our 2021 work. Ibsen had kind of similar qualitative ideas. I think we made it a bit more formal and general. So the idea is basically let's decouple these two things. Oh, one cool thing that I wanted to say, right? You know, in the previous talk, we heard about why is mean field scaling, why is setting the variance very low helpful for feature learning. So by the way, you just look at this term and you see the coefficient here is 1/n. It turns out that if you go to mu-p scaling, the 1/n disappears. And you don't have to think too much, and you see that, whoa, feature learning corrections become strong now, okay? It just comes out, technically you get a 1/n factor here in addition, but the definition of T gets another factor of 1 of n here, and you have a T squared. And so, you know, a lot of things here, no match with previous talks. So we're actually under, in the experiments I'm going to show you, that's what I'm doing. I'm doing mu-p scaling where this actually wouldn't contain 1/n. But anyway, it's still the same thing here. I'm going to look at this term and I'm going to try a mean field decoupling. I'm going to split it into quadratic terms that see all the other interaction terms as a mean field average. And I'm specifically going to use this decoupling. It turns out to be justified at mu-p for mean field scaling and works quite well even in standard scaling for many settings we considered. So I'm going to replace this by the mean field value of the T's, which is basically the average discrepancy, the error in prediction. This is just how it comes out. Plus, I'm going to let the T's run loose, but I'm going to take the average of this over the W's. So this is basically the kernel of the network. So what I've done now in this approximation is, let me, and by the way, there are other approximations one can use from this action. One is the kernel scaling approximation, which coincides with a lot of the things that Boris and Hanin is going to tell you tomorrow, I imagine, just reading the abstract. So we can also contain these kind of results using our physics formulas. There's no proofs, of course, but it works. So more technical stuff. What just happened? We replaced this by, we did this mean field decoupling, which means that this action can now be split into an action for the input weights that sees the average discrepancy and an action for the outputs that sees the average kernel of the weights. So technically, these are the actions, and they are decoupled. This one is very nice. It's just a Gaussian process. We can use all the previous approximations of that. This one is a bit trickier. For a linear network, it's Gaussian, and we can solve it, but we want to do better than that. We want to go nonlinear. And then it turns out that in many cases, actually, it's not always the case, but in many cases, you can approximate this nonlinear action using, if you're a physicist, a Hardy-Fock approximation, if you're a machine learning guy, variational Gaussian approximation, and kind of say that whatever complicated thing is happening here, it's close enough to some shifted Gaussian distribution of the W's. And then you get this bunch of equations that you need to solve. But before that, I'm going to kind of give you evidence. So this is kind of W's and other pre-activations for a nonlinear CNN. You know, they're pretty Gaussian. This is for real-world networks. You know, 3 out of 4 are Gaussian. This is Chengiz and Bordelon work, which typically are angry about us for this Gaussian approximation, but in some cases, even for a transformer, they see Gaussian, in some cases not, so it's definitely nothing generic, nothing completely generic, but it does work many times. And the last insight I'm going to kind of say is comes from symmetry. Because we're working in this disorder average setting, and remember the staircase function that we have that only dependent on a particular direction, the problem is completely symmetric for rotation around the teacher direction W star. And that immediately implies that whatever horrible mess self-consistent computation is needed here, it just depends on 2 parameters, because if you know this covariance matrix of the weights, you know the kernel. If you know the kernel, you have a Gaussian process and you know the discrepancy. If you know the discrepancy, you know what's the action, and again, you know what is sigma. So everything basically hinges on knowing sigma. And by symmetry, sigma has to be of that form. An identity matrix plus an outlier around the W star direction. There's nothing else you can write. Okay? And so we reduce this problem to 2 parameters, A and B, that we have to, that we can write nonlinear equation for and solve. So this is what I would call an analytic solution. I would say a nonlinear equation in less than 4 parameters. Let's call it an analytical solution. Okay, although it's a bit murky. Definitely, if the number of parameters start scaling, you know, larger than 10, 20, then you probably traded one hard problem with another. Yeah, sure.
Sorry,
This one.
Just when you talk about this expansion that you're mentioning in F minus Y squared, this is the Kanatar et al.
Oh no, so this is really understood. I mean, this is what I'm saying is after you do this mean field decoupling, you get 2 decoupled layers that see each other only through mean field values. One of them is a Gaussian process, and so for that you can use Kanatar's approximation. But it's all happening together now. Kanatar's approximation together with kernel adaptation approximation, and that's really a new result here. That's on our view that we finally, you know, stitched everything together, all these different approximations.
Do I have to swallow their assumption that you swallow?
Yeah, you should swallow that, unless you wanna. Yeah, I mean, until something better comes. I mean, I prefer to try to do prediction, and as long as it captures the qualitative phenomena, I would say, you know, let's start from there. So you think about any instance of your neural network that produces a function f of x. You take that minus y of x, and then you sample x from your data distribution. So this is a random variable, multidimensional, but this is a scalar random variable. The claim is that this guy is Gaussian. That's horrible. That's crazy, because y, for instance, can be a binary target, which is multimodal. So how on earth should that work? But the answer is that it works. Okay.
I appreciate your point that, you know, make predictions, see if it agrees. Is there some intuition for why it works?
Yeah, I would say that, you know, you can say that when you're learning well, then you sort of predicted much of the components, the multimodal components, and maybe what's left is just noise. But it's not entirely exact, right? So you just discrepancies. I mean, we are running their inference. You know, sometimes we hit the mark exactly, but sometimes you do see small discrepancies.
Your point, I guess it sounds like you're advocating the perspective. Take this assumption, mix it in with your kernel adaptation stuff, and just see if it agrees with experiments.
Yeah, exactly. Yeah, this is. Yeah, I mean, if I have a readable approximation, I want to use it. You know, mean field, you know, is not exactly true, but you know, see how much is used in physics. I'm not particularly tied up to exact asymptotic limits and things like that. So there are a lot of Gaussianities involved here. This is some predictions we can make here that show that you can learn the component and the pre-activations are Gaussian. This is This is an experiment and the theory I just described. Curiously, we're pretty close to a phase transition here. So if I change the makeup of my target just a bit, then I actually get something that looks like, in the log probability of the weight, something that looks like a second order transition. We have a paper about rocking that actually sees first order transitions associated with modular addition and things like that. So there is a rich phase diagram here. I by no means want to give a simplistic view that Fresnel adaptation and Gaussian approximation of pre-activation always works, but just, we can do a bunch of stuff and calculate. This is from the review for a CNN, which actually, even nonlinear ones, which actually turns out to be kind of simpler because you sort of can separate the linear space, interesting things happening in the linear space. So we can really show here change of sample complexity. The point here, nonlinear networks in a regime where there is different sample complexity and the axes match the theory. That's the take home message of this. And this, this brings us to a conclusion of the feature learning part. And of course, open questions. We don't understand what feature learning is in general. And one way to do that is start understanding like the equilibrium phase diagram of these things. So from studying this in the past kind of 3 years, we already found one phase where you have feature learning, but everything remains Gaussian. We saw first order phase transitions, which have a mixed phase and a non-mixed phase. There might be second order transition. Chaim Sampolinsky has a work where some neurons actually specialize with Alex, I forgot the surname, sorry. The works from OpenAI and Transformer Circuit also indicate that at some phases, features start interacting with one another and create these polygons in activation space. There is probably a zoo here, just as much as there is a zoo in a condensed matter when you start putting electrons in magnetic fields. And so there is interesting stuff to understand here. Can we understand feature learning in the neural scaling regime? For those of you who know that, that's interesting. We'll talk about neural scaling soon. Can we relate mechanistic interpretability with this notion of adaptive kernels or whatever more fancy technique we would discover? That's a very practically interesting question. It's not at all trivial because it requires us to actually go closer and closer to the underparameterized regime. And one of the questions, that's more qualitative is we know the limitations of GP, but we don't really understand the limitations of feature learning. I mean, if the neural network is this complete elastic thing that can adapt to everything, it should also overfit at some point. I mean, it cannot be a completely unbiased predictor of everything. So maybe feature learning is bad sometimes. Maybe it has some limitations. Maybe it ignores some signals in the data because they don't propagate well through the layers. So all of this can be studied by, for instance, extending, this and studying the 3-layer thing and seeing how feature learning propagates. So there is a lot of interesting stuff that one can do. No short of stuff to do in this field. So now let me take us down a bit, So when I'm in a somber mood, I think about this fact, that Andre was alluding to in the introduction. And because if you come from high energy, amazing predictions. Amazing work, you guys. The next matter,
I wasn't asking
okay.
for forefathers.
Right?
It's our forefathers.
Well, but still, as a field, you are now the keepers of the flame. And in condensed matter, we sometimes, manage to do something which is 10-20% from experiments, and we should be happy with that as well, given the lower modeling level. You want to do that? That's good. And so you come to this field with some, unconscious expectation that you're going to explain deep learning, right? You're going to apply your physics techniques and you're going to explain something in this field. And truth is that it should be quite impossible to reach this goal. And this struck me like 2 years after I entered this field. So let's assume, you actually solved the problem, not made it into a different complicated problem with matrices, but actually solve the problem. You know how to compute in pen and paper and understand why ChatGPT works. So the fact that you call your solution analytical means that it's O of one in terms of computation, right? But then you found an O of one solution to the optimization problem of ChatGPT. So you just saved all these GPUs. Moreover, you also have the solution. So the reason we have neural networks to begin with is we could never work out a solution for this problem. So on multiple levels here, it's completely impossible that we would ever predict anything directly relevant to the details of an experiment. Okay? So that's, yeah, so anyway, I'm leaving. I know so, but then you enjoy what you do, you know, so you find ways to rationalize it. And just as a contrast, you know, this is what I grew up at, you know, Steve knows that well, you know, you take a piece of metal, a piece of 2D junk, more or less, put it in a high magnetic field, measure the conductances, and it turns out that it's quantized to values of E squared over H times a rational number. And you know, this is absolutely fine for physics. You know, we expect nature to be generous and universal in this beautiful way, but it just can't be, you know. Deep learning is much more like biology than it is like physics, honestly. And they already gave away the Nobel Prize. Okay, so here is how you can you know pick yourself up from that. So you should believe somehow the toy models capture a greater truth. And you know, it's not if you start, you know, that can be, I mean that simple models, though they cannot explain the complex phenomena because it's made out of a trillion of components, they can capture one aspect of that. And then one other belief is that, which is, you know, you can ground, is that some aspects of DNN, you know, you can sort of decouple from the mess of training on data. For instance, initialization. Okay, so all these things about MUPI scaling, which we heard of, and even like the initial success of training deep neural networks by just understanding well how to make the signal propagate. So that's something that we can be hopeful of. Another is dimensionality reduction. You know, maybe, you know, we find that you can train batch size with learning rate, okay, in some regimes. And so you have to do less grid scan for parameters, okay? So, or maybe we find that, you know, some effective measurement like the 1-point function, 2-point function, and 4-point function of the field is enough to characterize a neural network. And then, you know, if someone comes up with a proposal for a neural network, you tell them, oh, leave me alone, it gives me the same 4-point function, it's probably going to do the same. It has the same problematic behavior. So there are things that we can sort of try to work around. And at least the third and the fourth point, in physics, we can sort of ground these using renormalization. Okay, so why are we exploring the 5 to the 4th theory? Because it captures all forms of Ising universality. So and so we don't need to understand, you know, the particular experimental setup. You know, we just ask, you know, what's the symmetry, and we're good. Dimensionality reduction, the fact that we don't depend on tons of hyperparameters, that's exactly the notion of RG flows and universality and relevance and irrelevance in RG. So if we want to put our money where our mouth is regarding point 1 and 3, we should study renormalization of neural networks and see whether we can flesh out some mechanisms of universality, relevance, irrelevance, etc. So this is kind of that would be the short last part of the talk, which is more related to the up-to-date things we're doing. This is collaboration with a bunch of people, including Gorka here in the audience. This is still unpublished, but we have some manuscript coming soon, hopefully. And so let me start now, fresh. You know, if you lost me before, you know, let's regroup. So in the natural world, we basically have 3 quite related notions. We have scale-free phenomena, okay, which I'm going to give some pictures of soon. We have power laws, and we typically associate that with universality. And the theory that kind of takes all these things together is RG. And here are some examples, you know, a river in Brazil, turbulence of water. When you take this image and enhance it, it looks like the same ensemble of noisy stuff. So turbulence is known to be scale free. And here is our beloved Ising model. Ising model. So let's enjoy this. So this is the Ising model at the critical point, and this guy is showing you 3 snapshots of the same system at different scales. Okay, can you tell which one belongs to which? Okay, so that's the answer. So these are the cool things we have with scaling variance. And then this, because you have scaling variance, you can imagine that any function that controls the correlation would have to be scaling variant as well, meaning it has to be a power law. So scaling variance and power law are naturally connected. And then this also is connected, as I said, to universality, because we know that if you take the Ising model with all local symmetry respecting perturbations, which are small enough, the liquid gas transition at the tri-critical point, quantum system with the Z2 symmetry, one dimension, they would all have the same power law with an exponent of 1/4. And that's, the hallmark of our arch. We cannot tell you a lot of all the interesting stuff. We cannot tell you what is this coefficient. We cannot tell you what's the critical temperature, but we'll tell you if you tune to the critical point in its analysis, you will see you 1/4, and we can actually predict that. And that's one of the pillars, I would say, of our understanding of condensed matter physics and high energy physics. Now let's go to ML and see how that breaks down or what pieces remain intact. But just even separating things is kind of interesting. So let's start with power laws. So data has a lot of power laws in it. It's quite amazing, actually. I don't know of one good explanation for that. You take War and Peace and you do the statistics of words. So this is just serial number of words, and this is the probability to find them. So this is probably J or something like that, the most probable word. And then this is maybe, I don't know, I. And then you gradually see that this thing typically follows a power law, which is pretty close to the threshold where it becomes unnormalized. So this is known as Zipf's law. You see the same if you take kernels on image data. Their eigenvalue distribution, it's not the same thing as word frequency, but their eigenvalue distribution is power law to an extent. And more remarkably, if you really go to large data set, this is the famous neural scaling law work, you see that the log of performance of these large language models improves as a beautiful power law with the amount of data points. So, who ordered that? Data is such a complicated thing, structures after structures, hierarchical things. Why would they arrange themselves in this power law fashion? And then why would the neural network learning on this data reflect the same or related power law? This is quite nice. And if we think that lessons from RG apply here, then these power laws may imply some self-similarity in some sense to be made, to be made clear, and maybe some universality. And that's I think kind of a beacon for theorists. A lot of people are interested in that. And then this is some low measure of universality. You take a transformer, you take an LSTM with sufficient number of layers, they sort of up to a point have the same slope. Okay, so these are kind of similar architectures of similar symmetries, and they seem to have a similar exponent. So maybe that's like the one before we had for the Ising model. So here are the big questions. Is there a scale associated with power laws in data and in learning curves? Are power laws indicative of universality? If there is universality, what is the minimal toy model? There is something we can all work on, and it would explain, maybe a bunch of models. And we won't care if it's radio activation or error for the data is a bit like that or a bit like this. Okay, so I think who heard about normalization group here in this audience? Okay, so apologies for those who haven't, but for the sake of time, I would just skip what is RG. I would just say broadly, it's a greedy integration out of the low variance mode in my probability distribution, to get a renormalized probability distribution for the remaining modes. once you understand that, this explains everything, but it's completely useless, I think, if you don't, but just, and then there is kind of a flow induced by the gradual integration out procedure. And then I'm gonna just kind of tell you what we did with rho. And maybe one point to be made is that one thing that RG is useful is for finite size scaling. You can do an experiment on a small system, very, very small systems sometimes. You know, I have a colleague that does quantum Monte Carlo on systems of size 8 by 8 by 8, 10 by 10 by 10, and 12 by 12 by 12. And they get the critical exponent up to like 4th digit, just because they have good extrapolation techniques from small size to large size. And the reason is that there is a deep connection between RG and finite size and scaling, and that allows you to have smart ansatz for your scaling functions. So that might help us scale, for instance, learning curves in this kind of dream between small models to large models. Yeah, so let's look at, okay, so let's start from our previous action, you know, we have this K, and if we diagonalize it, it looks like this. We go to the eigenbasis of K. And then as said, for real world data sets, lambda K drops like a power law, meaning that -1, it increases like a positive power law. And now let's, you know, just rewrite this a bit. Our previous action, where did it go? Here it is. We can now rewrite our exact GP action by kind of keeping only the truly quartic and above terms in the interaction term and putting out the linear part. We can write that as such a theory. There is a free part, which is a free critical theory that has a mass determined by the data. And that's really analogous to, in the Ising model, having here the K squared plus M squared, okay, the mass. And then we have an interaction which is unfortunately more complicated, but it's still local, for instance, you know, so it's not that bad. The term that's non-local is this. And so you can see here the, you know, you can see here what you want to do now, right? You want to basically integrate out the high K modes, which are very energetic and get an effective action. So we did that together with rho, and it turns out to be tractable and leads to this effective. So we're coming back now to the first part. Doing that leads exactly to this effective temperature, effective ridge, which stops the overfitting in the model as long as you're in high dimension and make these Gaussianity assumptions on the model. So you basically get a renormalization flow that's determined by a single parameter, which is the effective temperature, and you can track it because it's almost trivial. If you now want to go away from the Gaussian approximation, you can still do RG and you get interesting stuff. We don't have it under good control, but we do have some simple toy cases where you can see something richer happening than this. So we think this might be a formalism to do that. Nice. I'm basically done. Yeah, so maybe like the one of the main insight here is that the RG flow is tractable with a single parameter, and the data sets the mass scale. So I don't know how. I mean, this is not really standard graduate stuff. If you want to do RG on a massive theory, you can say, "Oh, what the hell? How can I do an RG on a massive theory? It's not critical." But the common practice is that you actually do RG on the very high energy modes that are much larger than the mass scale. On this regime, your theory is approximately critical, and you do RG up to the mass scale. So here, what sets the mass scale is the number of data points. So we get an interesting interpretation where the number of data points sets the mass scale in the theory, and so it tells you how low can you integrate down to. But it also now tells you something interesting. It tells you that, you know, as you increase the data, you basically flow to the UV theory. And if the UV theory is asymptotically free, that can be like an argument for universality. And this is a lot of the essence of what we're working with Gorkov, which is here at the moment, and we can talk with him about that later on. But this is already
Flowing to the UV theory, you just mean you can't integrate down as far, and so you're pushing up the cutoff.
Yeah, so you're going back to the microscopic thing. And I can tell you like a bit of a spoiler is that we see with the work with Lorca, it's still unpublished, that most perturbations to the model are IR relevant, meaning that if you sort of tuned your model such that it behaves well at low data, you know, all these irrelevant perturbations that you had to control would actually go away, and you will get something more universal as you go to large data. So there is some hope that one can use that to justify why large data models behave the same. But this is, you know what, this was important.
If you're not familiar with it, you might check out David Berman's work, which does the same sort of thing in the inference context where.
Yeah, no, we're aware of that. It is kind of in the same spirit, but technically at the end of the day, it's very different.
Yeah, exactly.
I mean, and we kind of focus on things that right now that enable us to actually compute something and predict. This is kind of our focus, but it's these connections to functional RG are definitely interesting, and it will be very nice to at some point connect them. Yeah, okay, so let me just advertise 2 things, and then I'm done. If you want your work mailed to 120 plus physicists, you know, consider registering to this mailing list run by Moritz Elias. And you just, you know, you just log in, and then you can post your physics for machine learning papers here. We recently have a review out, which surveys, you know, this bunch of works that kind of try to think about neural networks as field theories. So you're free to check that out. It covers it covers a lot of the topics in the talk. And yeah, I'm done.
Yeah, I'm just maybe got a bit lost. Very early on, you said that you were going to show you could just derive that essentially weighting on these high complex wiggly solutions was less in your framework. Do you mind elucidating that result?
The wiggly solution meaning that overfitting solution.
Is that because of the k to the -1, the high energy eigenmodes?
It is all related. If you don't have these many high energy modes, it won't work. Let me kind of tie it to the RG part. In the RG part, what we see is that the RG flow is basically telling you integrate all the modes up to those you can actually learn. Okay, and then even if you start from zero ridge, which is when you have these wiggly lines. By the way, also in kind of our lab experiments, right? If you add just a regulator on the coefficients, you don't get this wiggly line.
Yeah, because you have 1/λ plus.
Yeah. When you have a regulator, so basically here, what we're seeing is that even without an explicit regularizer, the neural network creates. So T is basically a regularizer in the Gaussian process. The neural network creates a regularizer, and you can even view that as an RG flow, where the low-lying modes that are just fluctuating independently or not learning anything are basically generating this fog of noise that becomes like an observation noise for the lower modes, and this generates T.
Okay, thank you. And just back to your figure where you compare the Gaussian process with neural networks, is it your intuition?
Which figure?
I think it was from that Google paper where they spent a lot of computing.
Yeah. Okay, yeah.
Yeah, is it your intuition from the experiments you've done, the results, that if you had a good set of handcrafted features for a particular problem, that the two should essentially converge?
Well, I mean, so here you have to be careful that you don't cheat, because you can take a kernel, which is basically Y transpose, right? And then you would learn anything perfectly. So the game here is a bit tricky, but certainly if you had a kernel that shows. So what's the right feature, which is not the target? And then, you know, you can say, okay, maybe the target's made out of 4 things. I'll make these my 4 features, but then it's again a bit cheating. So I don't know how to answer this. And I would certainly want to know what these features are, and probably none of us.
So when you're doing, can you explain a little bit more about how you think about decimation? So your field theory is.
Yeah. My field theory is made out of K modes, which are actually kernel eigenmodes. But this just serves as the starting kind of non-interacting part of the theory. So it's just like, let me gradually go there. Yeah, so maybe that's the best slide for that. So this is how you would do it in an Ising model, right? You would integrate out the high energy modes, the high K modes, to get an effective renormalization of this thing. You will get the Wilson-Fisher fixed point. What we're doing here is essentially the same. We're integrating out the high K modes, which are associated with very stiff modes of the kernel, but still there are many of them, so they have a collective effect. And we're gradually integrating them out, and we see that we can swallow up their effect by just a change of T. So it's even simpler than the Wilson-Fisher fixed point where you have to track R and U, or you have to track the mass and the interaction. You just have to track a single parameter.
So there's only one relevant operator.
Yeah. I mean, it's a bit tricky to say because what we do here is EFT. Basically, we integrate out and we don't rescale. Actually, the rescaling part, which is part of the work that Dorka is where you can start talking about relevance and irrelevance. So I would be a bit careful with that. I think they're actually, at least I can say that for this model, without any perturbations, we can track the flow. But I'm not entirely sure what the statement about perturbations, general perturbations.
So maybe it's not a but like, is it? Can you if you think of this that this is some different functions, can you like say approximately what would be the other function to get rid of
these high modes, yeah. So let's say for CFAR, it seems easy because if you look at what are the general kernel modes on CFAR, they do seem to correlate rather well with high frequency modes. So there I would say it's some sort of high frequency, low frequency thing.
high frequency
in pixel space, really, in the physical image space. Yeah,
in space time, and that's
space, two-dimensional space.
Like even yeah.
In really like vanilla image space. But what happens for language, for instance, might be something more related to the zip flow, might be related to like some words having,
like in this picture, there's no like it's not math. There's no formal thing you're doing with functions. There's no formal thing you can do with functions in some kernel approximation that you're doing here.
Well, so this is a kernel limit, not an approximation, but a kernel limit. But what I'm taking here from experiments, which is like the magic, is the fact that this thing behaves as k to the power of alpha rather well. So that the features might be complicated, it might have some implicit notion of scale that we're yet to understand, but at least I can play some formal game, pretending that this is k-space, and that seems to work out well.
You're assuming some parallel. So this is kind of like
because I see it in the data, yeah, exactly.
You're kind of like you're almost fitting Lagrangian.
Yeah, I have like one parameter I take from experiment, which is oddly enough the dimension, not the dimension, the strength of the Laplacian, the power of the Laplacian. But yeah.
Yes. So, I have really important that on this
Yeah. Yeah, exactly. So this is exactly what we're seeing. We're seeing here that as you do RG on this, you have a flow of this coefficient, which basically changes this T. Okay, and so you have an RG flow of the effective ridge. And what's nice is, at least in many relevant regimes, it flows to be big enough that you can now Taylor expand this exponent, and if you like, get to a free theory. So in some sense, it flows to a weakly interacting theory. It starts in the UV from a strongly interacting theory and flows to a weakly interacting theory. Yeah, so this is, where is the expression? So the expression is T at a particular cutoff scale is equal to T at, the true cutoff, let's say infinity, plus the sum of modes from and then when the modes are very dense, you can actually think about that as an integral, and that's a continuous thing. Sorry? T is a coefficient in my action, right? T T is exactly this coefficient over here is written as kappa, but T is this coefficient, and this coefficient flows much like U, the coefficient of the interaction in a Wilson-Fisher fixed function.
This describing our original.
Oh no, so this really doesn't touch the architecture. That's a convenient thing, although that might be more interesting, you know, if we can track such flows that, I don't know, leaky value goes to ready or something like that. That's here it really just tracks, if you want to kind of trace it back, it just tracks the effective noise of your training algorithm. Okay, so the T originally came from the stochastic noise you have for the training algorithm, like NTK, for instance, would have T equals 0. And you're generating this effective noise, even in an NTK setting. Okay, so originally, one of the reasons people got interested in this more complicated limit is that for NTK, this is the formula for prediction you have. T is equal to 0. We're stuck with no good approximation. And now what basically is happening, if this is the NTK itself generates a non-zero T. So if you want this coefficient flows from 0 infinity, we'll define it to a finite value.
Original architecture.
Oh, so that's how strongly each data point is pinned to the observation. Okay, so when you present the data, you don't have to ask the network to, you know, have it smack on. This would be T going to 0, will tell the network, listen, every data point has to be fitted perfectly. So what's happening during RG is that this gets loosened up a bit. So you're willing to suffer some difference there. And that's the meaning of T, the technical
Went to MSC loss.
Sorry?
Went to MSC loss. Or like in this.
It's like from a full constraint loss to an MSC.
MSC loss.
Yeah, it kind of makes the MSC loss more and more soft. Whereas a T equals infinity, the MSC loss is really like effectively a constraint.
So maybe going a little bit off out of this, but so in your Google study that you had, so the worst performance was for CNN with equivariance. Is there a mathematical reason or just simply the algebraic constraints of equivariance which spoils RG?
Is that like where the gap was large? Yeah, no, that's a fun thing. So they show it in that paper. There is a deficiency of the GP kernel of a CNN without pooling. That's the important thing. Coincides with that of an LCN, which is basically a CNN without weight sharing. And that has actually, even as a neural network, lower performance. So it just happens that some architectures don't translate well to a GP, or the GP misses out on a qualitative aspect. But once you add pooling, there is a difference. It becomes a very complicated kernel. They have to do horrible numerics just to calculate the kernel, but so there is a clear explanation actually.
So there's kind of an intuitive explanation why.
Yeah, and the reason is that you calculate the GP basically ignores weight sharing sometimes.
So that's kind of same for any equivariant, non-trivial equivariant.
Sorry?
Any non-trivial equivariant will have this weights which are related algebraically.
I think so, but if you have pooling, you wash that off. Yeah. And pooling is also useful for networks. It still gives you the right gradient in architecture space.
Both of the college people start. What I'll do instead is I'll ask you a question about crosstalk in But just a sort of big thing. So currently when Tim talks, he has a, so I'm just going to do cats and dogs because I think thinking about language that's much more complicated, like numbers of sequences and so on. So X is the space of pixels or something, numbers, right?
Yeah, it's a vector of pixels. That's it. Yeah.
Pixels that pi is pattern for all of them. Now, if we normally field theory is calculating things like pi of X, pi of Y. So the usual field theory ways, there's some notion that function pi is somewhat smooth, with the neighboring points, right?
Yeah.
And that's the notion that lattice scaling correlation lines.
Yeah.
Now, if we literally looked at pixels, because what we're really trying to capture is that when we look at a picture, it's like a cat or it's like a dog, is it really the case that the full space of assignments of pixels has that kind of smoothness that if you were to look at it, you would find that if there was a cat, you know, everything nearby that you could sort of deform to looks like a cat to us, or the optical illusions often rely on the fact that.
Yeah, I mean, I think like if you put reasonable amount of noise on a cat, you know, you would still recognize it's a cat. I think the problem is reversed, that if you just have geometrical constraint, if you're just willing to say a label, the right label is a ball around the images I've seen, that's going to be extremely inefficient at high dimension. So actually the kernels have to be very smooth in a way that they shouldn't be too sensitive to the Euclidean distance, for instance. So in RBF kernel, you know, these are the classical kernels people have used, e to the minus the difference in Euclidean space would be a horrible choice. And actually smart kernels actually give you a right similarity measure on the space of images that makes images with related labels seem also more close in terms of kernel similarity. But that really requires a lot of not necessarily a lot of smoothness, but a lot of non-locality. So this thing shouldn't drop out very quickly with Euclidean. And
That's really interesting. So you said noise will surely do it for cats. I mean, is this, so let's promote that aside. Because the other possibility is that cats and dogs we look at are generated, but you know, actually it's a much lower dimensional space of data. Yeah, I'm plotting it in space, but in fact the underlying space of parameters is actually much smaller.
exactly, yeah.
If that were the case, then if as physicists we wanted to, you know, you want to know in what space should I be trying to co-strain?
Right. So in a way, one of the lessons that if you want for this and from feature learning in general is that what is a kernel, right? A kernel is, you can always diagonalize it using Mercer's theorem and write it as some lambda of k and a set of features. So if you want, this set of features are like a nonlinear transformation, which should take you to this ideal space that separates cats and dogs, and focus much of your attention on these. So these, if this is the cat and dog function, for instance, and you only have a single eigenvalue, then this is the best kernel in the world. So what basically is happening during training is that both these features change and the lambdas change such that you accentuate the features or nonlinear feature functions of the data which compare images better. But this is something now we can ask the neural network, what are you doing by diagonalizing this kernel and sort of inferring what these features are? You can see some interesting things. At some point, it's hard to interpret because these are very high dimensional objects. But really a kernel kind of knows how to do that job if you just give it the right features. Because this, if you want, lifts you to a feature space, which can be very complex, very nonlinear. And then here you decide how you want to weight these features. And then if you're doing it well, you can see the similarity much quicker than you would with an RBF kernel or something like that. I just said the phi of k of x is a this can be the radius function as we heard in the previous talk. So this can be like a single lambda, this measures the radius function, and suddenly this would be the best kernel. So maybe we can have the neural network teach us that. And in a way, that's what the sparse autoencoders are extracting, but in a much more elaborate setting. So this is the finishing.